Hey everyone, so this is going to be lesson 6, all dealing with exponential functions. So in the beginning, what we're going to do is we have these two do now questions. What we're going to do is solve for the function f of x equals 2 to the x. And we're doing this between the intervals of -3 and 3. There's a few ways that you could do this. If you have a graphing calculator, you can put this equation in the y equals section. And then when you go to the table over on the right, you can see what all these values are. If you don't do that, then you could just plug the numbers straight into the calculator and see what you end up getting. So when you do 2 to the -3, you get 0.125. 2 to the -2, 0.25. 2 to the -1, 0.5, 2 to the 0 is 1, this one is 2, this is 4, and this is 8. From here, we're going to try to graph it. So it doesn't matter how you're going to do it. I'm going to skip every other line. So this is going to be -3, 2, -1, 1, 2, 3. And then up here, I'm going to just label 2, 4, 6, and 8. So I'm just going to plot the points. So to -3, actually, I'm going to start from the 3 side. 3 goes to 8, 2 goes to 4, 1 goes to 2, 0, 1. These, what I'm going to be doing is halving going up. So 0 and 1, half is right in the middle. 0.25 is in the middle of that. So it'll be a little bit lower. This one's going to be a little bit lower than that. So from here, I could just connect the dots. And my graph should look like that. Again, if you have a graphing calculator, you can see this for yourself. Down here, we have another function to graph. And this one actually ends up being pretty much the same thing, except now everything's flipped. 1/2 to the -3rd power will end up becoming 8. This one will become 4. This will become 2, 1, 0.5, 0.25, and 0.125. So again, you can either use the graphing function in a graphing calculator or just plug in 0.5 to the -3, -2, -1 power. Same thing with the graph. We have to plot our points. -3 goes to 8 this time. -2 goes to 4. -1 goes to 2. And it just looks like this. And now we end up getting the curve going the other way. So these are the two different types of exponential graphs that we can have. Down here, the notes talk about exponential functions. So exponential functions will always have this type of relationship. It's going to have some number raised to the x power. That some number, in this case, is represented by b. And it could be multiplied by the term a. A is the initial value. So if the graphs, or if our question starts with some initial population, initial value of money, that goes in for A. B ends up being the rate at which it's either going to be changing. So if B is greater than 0, then the graph will always be increasing, which is what we call exponential growth. If B is some number less than 1, but still greater than 0, so like a decimal, something like 0.2, 0.3, 0.75, then the graph will end up being decreasing, which is called exponential decay. So exponential growth, this was actually the first do now question. So this was number 1 from the do now, and the decay was number 2 from the do now. This makes sense because in the first question, B in that case was equal to 2, And then for the second question, b was equal to 0.5 or 1/2. One thing to note is that exponential functions like this are asymptotic to the x-axis, which basically means that it's going to have it's going to end up getting very, very close to some number, some line that's parallel to the x-axis. That line that it gets really, really close to is what we call an asymptote. So again, in our do now, we had a graph that looked somewhat like this, where it got really, really, really close to the x-axis. If we kept pulling it, going all the way into infinity, we would realize that while this does get closer to the x-axis, it never actually crosses it. There are some graphs where instead of it being the asymptote being the x-axis, where y equals 0, it could be some other number. Like in this case, it's raised by to some point. So it still looks the same way that we have in the do now. It still has an asymptote, but it's just got shifted upwards by some amount. All right. So we'll see a few examples of this. Exponential functions are very important. They become extremely important with things like money, you know, getting money from interest from the bank, house mortgages, house payments, you know, all those types of things, as well as population growth. You're going to be seeing a lot of questions like that in this section. So here's an example. We have this function, 400 times 0.85 to the 2x minus 6. Now, they want to know what the initial value of the function is. Well, what we do to figure out the initial value, that's when x equals 0. So if we look at our equation, plug 0 in for x, we get this. Now, 0.85 to the 0 power is just 1. So this becomes 400 minus 6, which is equal to 394. So our initial value is 394. The way you're going to do this is to, like I said, plug it into the calculator. If you didn't see that right away, the calculator will tell it to you, just make sure that you plug it in properly and you put parentheses around the variables. All right. Now what you have to do is figure out whether this is going to be exponential growth or exponential decay. Now, if you recall, we said before that b, which was the number being raised to some power, if it's greater than 0, it's growth. Sorry, not 0. If it's greater than 1, it's growth. And if it's less than 1, it's decay. The term that's being raised to the power is 0.85. Since that's less than 1, it's decay. So this would be exponential decay, since 0.85 is less than 1. Now the next part is where we're going to actually graph this. So again, you're going to have to use a graphing calculator. If you have one, you might have to reset the axes and set it to zoom fit. But the way it's going to look is going to be about, I'm going to eyeball some of these numbers. So that goes there. And I'll just do this point over here. And it's going to end up following some curve like that. Probably could get something a little bit better, but that's pretty much good enough. So again, you can check this with the graphing calculator or some sort of graphing program. All right. So these are two equations that you should have learned in Algebra 1, the exponential growth and exponential decay equations. So what we're going to end up doing is in the following examples, they're going to give you information, either the initial value, the percent rate, the final value, or the amount of time, and we're going to plug it into these equations to come up with some function to represent what's going on. All right. So the main difference is that if it's growth, we have a positive here, and if it's decay, we have a minus. All right, so down here in question 1, it says the population of Babylon in 2016 was estimated to be 35,000 people with an annual rate of increase of 2.4%. They want an equation for this. So this is going to be related to my R. This is my A term, my initial value. And I think that's about it. So what we're going to do, this is, because it's an increase, we know that this is the growth. So this becomes y equals a times 1 plus r to the x power. A in this case is going to be 35,000 people. Now, the 2.4, the rate, always has to be done in decimal. This is not in decimal form. This is still in percent. Remember, the way that you write a percent is that you move the decimal place over 2 times to get something like this. 90% is equal to 0.9. 70% is equal to 0.7. 5% equals 0.05. So 2.4% would be written as 0.024. We're just moving the decimal place over 2 times. And that's going to be raised to the x. We're going to want to actually add these. So the 1 plus 0.024, we can combine that together. And we get our final function as y equals 35,000, 1.024 to the x power. All right. Now they want us to estimate the population the year 2020 to the nearest 100 people. So let's just figure out what the population is according to this graph or this function in 2020. So since these numbers were given from 2016, that's a time period of 4 years. So we're going to plug in 4 for x, 1.024 to the 4th. So you go to your calculator, you plug this all in, and we end up getting 38482. Now, what's important is this. They want us to round to the nearest 100 people. So that means I have to round this number, the 4, which is in the hundredths place, either up or down. Since the number to the right is an 8, this gets rounded upwards. So this becomes 38500 people. And that's it. All right. We'll see another example. So here's another one. Similar idea. They want us to figure out what the final value is after 4 years. So we do the same idea. Here it deprecates. That's just another way of saying that it goes down. So this is exponential decay. So we're going to end up having the minus r in there. Our initial value is 35,000. And they said that the rate is 5%, which would be rewritten as 0.05. So I do 1 minus 0.05 to the x. And then I'm going to just simplify inside the parentheses. 1 minus 0.05 is 0.95. Now it says that they want us to figure out what it is after 4 years. So I'm just going to plug 4 in for x. Plugging all this into the calculator. I end up getting this in my calculator. Now, again, I have to pay attention to what they say afterwards. So once I get my number, I just look to see how it needs to be rounded. It needs to be rounded to the nearest cent, which is right here. So this becomes that, because the 8 on the to the right of it, the 1 becomes a 2. So this is my final answer, 28,507.72 cents. Right. Now here's another way that they can ask these types of questions. So here, instead of asking for y, they actually gave us y. So they gave us the initial value and they gave us the final value. And here they're looking for the rate. So we're looking for r. They said that this is exponential growth. So this is going to be using this equation. Y is 135. A is 100,000. I don't know what R is, and X is going to be to the 5, because it's 5 years. Now, this is actually relates exactly to what we talked about a few days ago, yesterday, in fact, where what you're going to do is solve this for R. Now, the first thing that we have to do is get the term, this term, by itself, because it's raised by the power. I'm going to do that by dividing both sides by 100,000. So this ends up becoming 1.35. Just like we talked about before, in order to move 5 to the other side, I do the reciprocal. So the 5 that was originally on the right moves over to the left and is written as 1 over 5. In the calculator, I'm now going to put 0.135 to the 1/5 power. And this becomes 0.0618588759. I can get rid of the parentheses now that the exponent is no longer there. So I have 1 plus r. I can subtract the 1 over to the other side. And I get r equals 0.0618588759. Now they want it in the nearest percent. So I need to move the decimal place 2 times, 1, 2. 6.1858759. Now I need to round this to the nearest percent. So since that's a 6, the number to the right is a 1. This just becomes 6%. And you can double check it yourself by using our original equation, plug in 6% in for R, and you would see that we would get the same answer that we got before. All right. Here, so what we're going to do here, they tell us that this is going to be an exponential decay relationship. Once again, we're trying to figure out the rate to the nearest percent. So our y value, the final value, is going to end up being 18,000. The initial value is 34,000. And x is going to be the 7. All right. So we're going to do the exact same steps from before. We're going to divide both sides by 34,000. This becomes 0.529411767. To move the 7 over, I do the inverse of that exponent to the other side. So raise this to the 1/7 power. And this becomes this. Now what we're going to do is subtract 1. Now here's the weird thing. We have a negative number, but we also have a negative in front of that r. So we could just divide both sides by -1 to get rid of that negative. Once again, because I'm looking for a percent, I need to move the decimal place over twice. So you get r equals 8.68503.833. This time they want the nearest 1/10 of a percent. So that's this number right here. The number to the right is 8, so that rounds to a 7. So my percent is now 8.7. Now you may notice that every time I do the math, I keep writing the full number. That's because you don't want to round it right in the beginning in case here it's rounded to something different than what we normally do. So they don't always round to the nearest whole number. Sometimes it's to the nearest 10th or 100th place. So I always recommend that you keep the numbers all the way through, especially on the calculator. So try not to round your numbers too much. All right. So here it wants to know how this could be evaluated using properties of rational exponents to get an actual number. So really, this is just asking how can we do this by hand. The way we're going to do this is by rewriting this in root form. So I can actually say rewrite in root form. So this is going to look like this. Normally, I would leave that power to the fourth power underneath the radical with the 8, but right now, just to make my life easier, I'm actually going to keep it outside. Then what we can do is do the cube root. So -8 to the cube root of that. Basically, I'm looking for a number that if I multiply it by itself 3 times, I get -8. The only number that works for is -2, because -2 times -2 is a +4. Multiply that by -2, and I end up getting -8. So -2 cubed is -8. I still have the 4 on the outside, and then do the 4th power. So what I can now do is just do this to the 4th power. Again, I can look back to here. If -2 to the 3rd is equal to -8, -2 to the 4th would be -8 times -2. So the negatives cancel out, they drop, and what we end up getting is 8 times 2, which is 16. So -8 to the 4/3 power is 16. Okay. All right, so here, another money thing. So they want us to figure out the rate of growth, the nearest percent. So let's see, it says that it's exponential growth. So we're going to use this form. It was originally 1.25, but is now 8.75. I'm looking for the rate. So I'm going to leave that as R. And they said that the time frame is between 1966 to 2015. If I use a calculator, I get this is 49 years. All right. So from here, I do the same thing that I did in the previous examples, divide both sides by 1.25. So this becomes 7. Do the reciprocal of the exponent to move it over. So 1 over 49. So 7 to the 1 divided by 49 ends up getting me this number. Subtract the 1 over, and I end up getting 0.04055342. Move the decimal place over, so it's 4.05115342. They want it to the nearest percent, so I need to round that 4. The number to the right is 0, so that 4 stays where it is. So I end up getting 4%. All right. And let's see. So here's the next question. So for this, we have a laptop computer that's losing its value every month. So this one we actually, we might have to be a little bit careful. We'll keep an eye on it. So let's see. The value of the laptop when it was purchased. So based off of the equation, the initial value is going to be this term. So it was initially $3,800. They want the decay rate. So because this is the decay rate, this is going to be basically modeled by this equation. So the 0.92 is the 1 minus r that we have in the exponential decay. So from here, I can do what I did last time, subtract the 1 over. I end up getting negative r equals negative 0.8. Divide both sides by negative 1. I get r equals 0.8. Sorry, 0.08. And then move the decimal place over 2 times, and I get r equals 8%. So that would be the decay rate. And now they want us to graph this over here. So let's see. You can, like I said, use some sort of graphing function. 0.92 raised to the x power. I don't really need, okay, so 0, do that, that's 1. I'll only do up to 5. I don't know how many. I guess I'll do it to 5. And then over here, so I'm going to have to go all the way up to 3,800. 1, 2, 3, 4, 5, 6, 7, 8. All right. So since I need to get to 3,800, there's 20 boxes. So if I divide each, if I divide 3,800 by 20, I can figure out that every box is going to be 190. So that's 190. The second box will be 190 plus 190, which is 380. Now I'm not going to actually label all of them. I'll only label every other one. So that would be 760. This would be 1140. This would be 1520. 1900. 2280. 260. 3040. And then the last one, 3420. Over here, let me just double check real quick. All right, I can keep going for a bit. All right, so what we can do is plug a lot of this stuff. Like I said, use the calculator for this. So at 0, it starts up here. At 1, it goes to 3,496. So it's a little bit of eyeballing, but you know, it's going to be right around there. 2, it's 3216. So that's going to be about there. Number 3 is going to be 2959. 4 is 2722. 5 is 2504. 6 is 2304. So it's going to be around there. Just curious, this is going to go up to 16, which is right about here. It goes up to 17, which is right about there. So you may notice that this graph doesn't really look too exponential. That's mainly because the numbers down here probably should have been much bigger. Most likely you would have wanted this last number to go all the way up to about, to about 80, it seems. Yeah, I think if you got to about 80, it would have looked a lot more exponential. So down here it says, how do you figure out the scale? So I guess a more appropriate way of doing it, rather than how I did it, was to look on the calculator. To see where the graph becomes smaller. So for here, at 0, it started off at like 3,800, and then by around 80, it gets all the way down to 4. So compared to where it starts, it's extremely smaller. And then divide that by the number of blocks. So if we were doing it the other way, we would have taken the 80 divided by 20 blocks and got that every block should have been 4. So instead of this line being 1, this one really should have been 8, 16, 24, 32, and so on, all the way up to 80. The y-axis is a lot easier. This is just look at the initial value and divide that by the number of blocks. So again, it was 3,800 divided by 20, got us 190 per. So it's always good to make a table. So again, what you probably would have wanted to do, X and Y, 0, 8, 16, 24, 32, going all the way up to there, and then recording the values that you have over on the side. So I'm going to try and get some of these numbers in. So 32 was 263, 24 was 513, 68. This one was about 1,000.9. This one was about 1950.2. And this one was the 3,800. I'm sure if you graphed these values, you would see a much more pronounced exponential decay. All right, that's it. Don't forget to answer the rest of the questions. If you have any concerns or questions about this, please let me know as soon as possible. Otherwise, good luck and have a great day.